Hello, everyone. Thanks for the committee. And today I want to talk about the HermesDB, which is the OLAP engine integrated Presto with lucene-based. Okay, before our today's topic, please allow me to introduce myself. And after graduated from the school, I worked for Hulu Beijing and then joined in ByteDance, mainly focused on OLAP engine like Spark, Presto, and some Clearhouse. But last year, I left ByteDance and joined in Tencent, but still working on OLAP, both open source like Presto, Doris, and self-developed. And if you are interested about my topic, you could send any question to my email or just search my name directly in the Presto DB channel of Slack. Okay, here is our today's agenda. First of all, I want to talk about the background about HermesDB. As we know, during the data warehouse area, we have so many demands from users. For example, we will have mass data like 10 billion rows, and the user wants to index on arbitrary columns, not a specific column. And besides, they also want real-time ingest, and they want different indexes for different column types. Except their data, they also have some performance demands, like they want to very low response time, like second level, and they also want huge ingest, especially for the real time, like 100 billion rows per day. So which engine should we select for their data warehouse, Elasticsearch, or only the pure Presto or Impala or Clearhouse? Their Tencent answer is HermesDB, which is a self-developed data warehouse. The history is here, and we could see that HermesDB started at 2013, and it has about 10 years histories. At first, we only focused on the basic retrieval, so we use the inverted index. But after 10 years development, we will have so many new features like we support mass data, we support real-time ingest, and recently, in recent 2 or 3 years, we support full OLAP. And at first, we introduced Spark for our flat OLAP engine, but you know, Presto is much efficient than Spark. So in last year, we introduced Presto. Okay, so currently we have about 5,000 loads in Tencent and about 10 million queries per day. It used in wide usage. It had a wide usage in Tencent, like Tencent Ads, WeChat Pay, Tencent Game, and so on. Okay, let's start our second part, storage. You know, since it's a lucene-based query engine, storage is very, very important. Here is our basic architecture. You could say it's the storage and the computation are separated. First of all, we use our worker to compute our basic data. But our storage could store at a local disk or distributed storage like HDFS, Ozen, and Ceph. So different storage will provide different functions. So the user could choose both local storage or distributed storage due to their goal for low latency or low cost. Besides, we also separate hot data and cold data in different storage to give a user low cost maintenance. Okay. Here is our main storage features. We use column-oriented and index to meet different user demands. For example, user will have some high QPS demands or low response time for huge data, or cost-friendly for mass data. Currently, we support different columns like retrieval, which will provide a low latency, and sorted, which we could store mass data. And we also support a high compressed efficiency, which is cost friendly. Besides, we support different index like square index, skip list index, inverted index, and so on. Over here, I will give you some examples. And for example, for retrieval column, we will have a very low response time, and we will start this column is mainly used for the media data, and the query should be not complicated. It should be a simple query, like just select a filter query with some simple aggregations. But their response speed is very fast, and our duplicated rodent index size is about 40%. It's not very big. It's good enough for our some situations. Okay. Besides the retrieval column, we will also provide like sorted columns. It will store mass data much bigger than the memory, but it could use other accelerations. And we use this. We implement this feature by sorted columns, and we index both on data and offsite. After these optimizations, we could get about 10 times the speed up. Okay. Besides of all, we will also support some index like the inverted index, FST key index, which is the extension of the tree. It will build a DAG for the string types, and all strings share the common prefix. It's very efficient. Besides, we also support the KDB index, which is very useful for the spatial queries. Okay. After introducing the basic storage, we will talk about the main topic, computation, integrated with Presto. Here is our basic computation arc and the main feature dynamic router. You could see HermesDB supported different prerequisites like JDBC, HTTP, and gRPC. But during the media layer, we will have a SQL router. For some simple queries, we just use the native engine of the HermesDB, but for some full OLAP, like the complicated queries with joins, with sub queries, and complicated aggregations, we will use Presto engines. And at the bottom layer, we could combine the native worker of HermesDB and the Presto executor in a single JVM on the same node. Yeah, so they share memories and they share CPU resources. Okay, first of all, let me introduce the native engine. Native engine is very simple. It's a gather scattered model, which means that it will read the data from the HDFS or local file. It will get the index and the term value. And the ULIN in all the HermesDB workers, and at last, all the data from the workers will send to the Hermes server to do the final aggregations or final unions. And at last, we will get the result like the maximum of the column A or sum of our column B and the column of our column C and so on. These aggregations use the indexes, since we will store the maximum, sum, and count on for each column in our HermesDB. Okay, but the most important thing is the Presto engine. You could say if we make some complicated queries, we will use our Presto engines, and it will route a query to it. Here we implement many features in our HermesDB with Presto. First of all, we need to push down the filters into HermesDB, right? Since push down is very important, especially we regard HermesDB as a connector for Presto. But it's quite different with the origin push down. As we know, we need to push so many operators into HermesDB, like filter, like top n, like the sorter. Yes, if we implement this push down as the usually ways, we need to write at least 3 Presto rules, Presto optimization rules. It's very complicated and is need to visit a tree, the AST tree, 3 times. It's low efficient. Here we use a stack to implement this rule. As we know, if we want to push down some operators like a partial AGG, like a filter, and scan into a single Hermes load, if any one load, for example, if filter could be pushed down the HermesDB scan load, which means that all the loads above the filter should not be pushed down either. So which means that we could use a stack here, named the query generator, which means that we just visit a tree from the push and to the bottom. And if we met some load, for example, the AGG, we will need to push it. We need to check it is valid to push it down into the HermesDB. If it's valid to push it down, so we push it into the stack. Okay, but if it's not valid or it's invalid, we need to clear the stack and continue our searching progress. And when visiting this for tree, when we are push it into the stack or clear the stack, and until we met some Hermes table scan load. And during this time, we need to squash the whole stack, and all the nodes should be squashed into one node, which is a new Hermes API, which means that we could push all these 3 Presto operators into single one. This way, we could implement push down for HermesDB. It's quite simple since we need to just visit this tree only once. Okay. Before this, we also implement some other optimizations like data transformation between HermesDB and Presto. As we know, we need to build a Presto block for the further computation, right? Usually we use block builder for different types like the int type, long type, and string type. But we found that the block builder is interface and it's quite low efficient. We found that for Presto block, there are only 2 arrays. The first array is called values. It stores true values for the data. And the first array is the second array is nonce. It means that whether this row is long or out of. Okay. But for Hermes data, we also have the long array values. It's a result of Hermes API, which means that we could just replace the values with Hermes values. But Hermes doesn't have its long values, but it doesn't matter. And during our implementation, we implement a vectorized API for creating its long values, which means that we could construct our Presto block directly without calling the block builder. So here is our benchmark. You could see your directly model is faster than the block builder with about 20% improvement. Okay. Besides, we also use some other optimizations like Java Vector API. So some of you may know this feature is incubating since JDK 16, and in Tencent we use our Kona JDK, which is based on the open source JDK 17. For Vector API, it is some Java Vector APIs which could call the SIMD extensions of the CPU. For example, here is a single example. Here is a Scala version for some computation with multiplication plus and some other computations. But during our another computation is a vector computation. It will regard the whole array as a vector, and it will call the related API like multiple and add and negate. So this will accelerate our computations and it will use a full resource of CPU. Okay, and here are some examples we implement the vectorization with the Java Vector API. It's the origin version. We need to decode our Lucene data from the encoded version to our direct version for Presto computations. And here are our vector API versions. You could say it's quite huge. But we don't want to talk about too details about this code. We just want to talk about some information for if you want to optimize your Java program with the vector API. First of all, you need to do a loop enrollment. You need to enroll this loop as much as possible. In Presto, we enroll this loop by 4 times. Besides, you need to unify the vector spaces. For example, different vector has different type. For example, here are int vectors and long vectors. But in this origin method, it also has a long type and int type. But according to our test, you had better use only one long spaces type for the whole computation. You had better not exchange the different vector types since it's very low efficient. The optimization 3 is that low boxing or unboxing. For example, here we need to use both unboxing types for our computations. Not use you need to use a primitive Java type, not a class type. Okay, and low object creation. ID creation for this computation should be outside the functions. And besides, you need to reduce the function call, and this will save a lot of times and help you accelerate your computation as fast as possible. Here are some computation benchmark for our Java API. You could see that it accelerates at least 40% for our origin versions. Okay. Besides, I also did some other optimizations, like the sequential memory access when converting the corresponding index to our origin string. At first, we store Hermes data in the index and dictionary, especially for the string types. But at the final stage, we need to convert the index back to a string, since we need to display these strings to the users, right? But we found that it's very low efficient since the string are disordered, so the index are disordered too. So we load a dictionary into a memory, and it's a random access for the dictionary, and it's very low efficient. So we find a solution. Before we access the dictionary in this step, we will sort the index firstly, and then we will search the dictionary in the memory. And after we convert them into a string, we will reorder the strings to the origin order, and it's much faster. Actually, in our online test, we reduce 30 seconds queries to about 11 seconds. Okay. Besides, we also suggest you to optimize some hot functions, especially we have some functions with single call for each tuples. We react these functions as a batch call, like Presto does in. So it will also accelerate our computations. So after these optimizations, how is the result? Yes. So here is the last chart. We need to give you some benchmarks. Here we use the star schema benchmark. It's a very famous benchmark, and we choose the table means lambda flat line order. It's a big flat tables, and here we compare the HermesDB with optimized HermesDB. You could see no matter the 100 million rows and the 60 billion rows, it will have about 10% improvement. Is very significant, especially we did a very especially we developed very few codes. Okay. Besides, we also compute our HermesDB with Clearhouse. You know, Clearhouse is very popular in recent years since it's much faster than most MPP engines. But you could say in most scenarios, our HermesDB is much faster than Clearhouse, except a few queries like Q4. But in most cases, our HermesDB is much faster. Except this, you could mention that here is QPS is 1. And if we increase the QPS at 220, you could find that the Clearhouse increase query time at senior at 9 year, but our HermesDB is very use very prudent times to extend our QPS to 20, which means that HermesDB will have a better performance on a high QPS scenarios. Okay, so the future plan, and we want to deploy our HermesDB on cloud service. Maybe at the beginning of next year, you could see HermesDB at the cloud service like Tencent Cloud. Besides, we also want to make HermesDB open source. And for some performance, we will continue our vectorizations. We will use some high performance vectorizations to accelerate our HermesDB. And besides, we will also build some HA features for our HermesDB and some memory management of it. Okay, so that's our things I want to share with you. So if you have any questions, you could raise it up in the chat or send to me my email. Thank you. Okay.
Thank you, Yue. Wow, that is some really impressive stuff that you guys have been working on over there. So very, very good to see. If anybody has any questions, feel free to drop them in the chat right now, either the chat or the Q&A. I think you also said they can email you if they have any questions. I don't know what the best email is, but if you want to drop that in there, that's good too. And I think, let's see here. Is there a question that's come through? Okay, that's Rachel talking. So this was our last session. Yue, thank you for closing it out so strongly. Really great stuff that you're working on with the community. Really excited to see where it goes. And thank you so much for sharing.
Thank you. Thank you.
All right.
Bye-bye. Bye-bye.
Bye-bye.